Okay, so up next, we have Continuations and Parallel Proving by Frank Laub at risk zero.
Thank you. All right. Hey, everyone. I'm Frank Laub, CTO, co-founder at risk zero. I want to talk to you today about continuations, which is a way for us to make ZK scaling, ZK proofs scale, and make them run in parallel. So yeah, if we look back, it's sort of like how we got here. We found that we could do verifiable computing by having sort of an economic incentive model to basically get lots of parties to, run a bunch of computation, and it's not really verifiable, but it is sort of trusted in the sense that you could get lots of parties to agree on doing these computations together. But there's some problems with this approach. You can't do really simple computations. They lack high frequency. It's kind of slow. It doesn't scale very well, and it doesn't deal with private data very well. So okay, here comes zero knowledge proofs. Great, wonderful. Except that they have a whole bunch of problems in terms of writing circuits. It's very difficult to do. Only certain people in the world can kind of do that. They have a lot of overhead, and they don't really, they're not super powerful without a whole lot of work. So if we look at kind of what's been successful out there, open source has taken over the world. Consumer hardware is really useful. It beats big iron. When you want to optimize for programmer productivity over runtime, usually it's the programmer productivity that kind of wins overall. You can get your things to market faster. You can develop faster, and standards are good. Generality is usually better than specific over the long haul. I kind of look at ASIC versus CPU. At first, there was lots of ASICs in order to solve problems, but it's sort of we've moved towards the generic sort of CPU is now powerful enough to actually solve lots of the problems that only ASICs could have done in the past. Scale matters. So if we look at like what it takes to scale these proving systems, the major constraint seems to be around the number of constraints in the system. The cryptographic foundations themselves are actually hard to make run fast, as we've kind of seen. And so, we've been looking a lot into using recursion to kind of solve these kinds of problems. But we have a different kind of approach, which is not really at the prover system level. It's more of an engineering kind of approach where we can basically take a big, long execution trace, split it up into different chunks we call segments, and then each segment is its own proof. You just run each segment as its own proof. It can run in parallel, and then when you're all done, you can roll up the result using recursion. That's the basic idea behind continuations. So in our zkVM, we can basically determine where those splits ought to go automatically. The segment size is basically configurable. It has to be a power of 2 because we're using sort of an NTT. It's a Stark-based system, so we do have to have certain limitations there, but the segment size is something that you can pick, and that is important if you're running on low memory devices, or if you have more memory, you can turn up the segment size. And what this gives us is the ability to run each one of these proofs in parallel. There's also this interesting feature where users can actually pause the execution of a program and then kind of continue it later on. And that's kind of useful. One thing I like to think about for that is sort of like for zkML use cases, where let's say I wanted to load all of my weights in as sort of one program and then pause that, and then have lots of other users continue that program doing their own inferences from all those weights that have already been loaded into the program. So you kind of amortize the cost of this computation across lots of different users. This is kind of an example of the code that we have for the Rust API, or to be able to interact with the zkVM. you construct, you can add your inputs to the program. You give it an ELF binary, which is basically just RISC-V code. Anything that compiles into RISC-V, the zkVM should be able to execute. And then you can basically say, okay, now go and create me a session, which then returns, internally constructs a bunch of segments, and then we ask the session to prove. You get back a receipt, and that receipt you can verify. So yeah, there's basically two phases to the system. One is the execution phase, where essentially you take your execution trace, and we're going to basically interpret all of the RISC-V instructions and generate the execution trace. And as we're doing that, we're going to find out where the split should go. And then the second phase is the proving phase, where, okay, now I've got all these segments, and I can treat each segment as a totally independent proof, and they can be run in parallel. Yeah, and then at the very end, you can optionally do a roll-up where you take all of the different segments and make a succinct proof out of it. So the key thing here is to figure out how to make sure that our memory images have integrity, that they're not getting, they're not getting fooled by the host isn't sort of like making modifications. So we want to have a Merkle-ized memory image that basically checks that the pre and the post states are valid. And so this is kind of an example of what that looks like. So again, there's the pre-flight, which is sort of this execution phase where we want to go through and just run the program sequentially and generate all of the different segments. Then once I have my segments, I've got the different the states of memory, A and B and C and D and E. And at the end, I want to basically show that I'm going from the very first state that I know of, A, and reaching the E state. And so, yeah, we have these leaf proofs here at the bottom. In this case, it's at the top. And then we run these join recursive circuits, and at the end, we get a final succinct proof. So we're borrowing some ideas from operating systems. The idea is that you can use paging in order to kind of summarize what's going on for an entire memory image. And so take my user memory and some system register information and split that up into 1 kilobyte chunks, 1 kilobyte pages. What I can then do is hash each one of the pages, and I end up getting an array of pages, a page table. And I can keep doing that until I get a final entry at the end. And what that ends up being is a Merkle tree with, however many hashes I can fit into a single page. I think it's about 64. So it's a kind of a very branchy Merkle tree. It's not binary, but in effect, you get a Merkle tree. And at the end of the day, I can then use this image ID to sort of compare different memory states. And the nice thing is that I only have to, when I'm computing this new image ID, I only need to do it for all the dirty pages. I don't need to do it for every single page in the entire memory image. I only need to keep track of sort of which pages were touched in that given segment. So it's kind of a nice performance feature there. So what are the kinds of things we can do with this? We already have a zkEVM demo. So for us, we can just take Reth, which is a Rust implementation of the EVM. It compiles into RISC-V. It took us about, 2 or 3 weeks to basically get an EVM implementation running within our zkVM. Same thing with WASM. We have a WASM interpreter that can basically just run all the WASM code inside the zkVM. We've also built a central limit order book application. There's multiplayer games we've done. One idea that we haven't yet gotten to, but I think we're getting closer to being able to do, which is running basically all of GCC or whatever compiler you want inside of the zkVM, and that kind of gives you a solution for software supply chain sort of verification. So that's basically what our continuations system is about. We've just launched Bonsai, which is basically a prover service that makes use of continuations and roll-ups. So we now have API keys that we're handing out to developers that want to go try it out. We're just kind of doing a slow rollout of the system. And so here's various links that you can go and get more information about that. And with that, that's it.
Hi, hello, thank you for that. It's super interesting and very relevant and helpful for me. I saw a tweet go out that there's like 2 megahertz something was clocked for RISC-0. Can you talk more like what about that benchmark?
Sure. Yeah, so recently we've been able to run, I think this is on that EVM example that I talked about. We can run an entire block in about 30 minutes. Basically, the idea is that we have the execution that runs at around 30 megahertz right now, the execution phase. That's kind of like, it has to be done sequentially, so you have to wait until that's done. But after that's done, we have about 100 GPUs that we have in the cloud that we can basically just run all the different proofs on. And when you add up the numbers, you get, 2.5 megahertz is basically where we're at right now. We think we can get about another 10x or so. There's a whole bunch of different places where we think we could do better optimizations. We have a bunch of GPU acceleration currently, and we think that we can, improve that quite a bit. We have the recursion circuit takes about 4 seconds right now, so.
Hey, thank you so much. I'm curious, what are some of the risks of breaking up the execution and proving in parallel?
The risks. Well, I mean, as long as the memory, like the host can't really, the memory image ID guarantees that the memory can't be tampered with between segments. I can't really think. Do you have any ideas in mind that you're? Yeah.
Not particularly. I imagine it would have something to do with the image maybe not being done correctly. But I noticed you mentioned that for certain parts of the EVM, you have to prove sequentially and not in parallel, right?
Well, yeah. I mean, the execution phase runs all sequentially. So yes, there's, when you're interacting with the host could lie to you and basically give you bad information. So you need to basically verify that that information is correct inside of the zkVM. But that's kind of a basic sort of constraint of zkVMs in general, I would say. Yeah.
Hi, thanks for the talk. Can you speak a bit to the verifiable GCC compilation that you mentioned before? In particular, like how you're dealing with all of the randomness that's happening, because from what I'm aware in like reproducible builds, right, this is often like the big problem, and how are you dealing with that here? Thanks.
Yes, so I think the idea here would be that, I've got, assume that you start with a memory image that contains, say, your source file, right? You've somehow loaded your source file into memory. Let's say that you've got a hash of that source file or something. Everybody agrees on, before you start, on what that source file is, and we all agree that we're starting from there. Then the idea would be, okay, now I'm going to run GCC. I'm just going to compile GCC for RISC-V. I'm going to run that inside the zkVM. So now, you're attesting that there's a translation that went from source code to some sort of whatever output, whatever you're compiling into. It doesn't even have to be compiling to RISC. You could be compiling to whatever target you want. And at the end of the day, you get this ELF binary or whatever the output is. You can now attest to this ELF binary and say, okay, because I ran the entire build process within the zkVM, you've now verified, you're now attesting to that now maybe there's bugs in the compiler. We can't really necessarily say that isn't the case, but at least from the reproducible build point of view, if somebody gets a binary along with a proof that says, hey, this source file was transformed using this compiler and it turned into this binary, and here's a proof for all of that, now everybody can just rely on, say, the hash of that proof or, you know, something like that. And that's, yeah, that's the basic idea. And then you can just kind of build up your whole, you could do libraries at a time and eventually build a whole application out of all the components and all that kind of stuff. So, yeah. We're not quite there yet because the zkVM only has about 192 megs of guest memory that's available. I think if we wanted to run GC, like simple programs, we could probably fit within that, but larger programs, you know, we have a future version of our circuit that should allow for the full, like 4 gigabytes of RAM kind of thing. But
awesome. Thank you, Frank. Thanks.